So this is 6.4, Logarithmic Graphs. And let's take a look at graphs throughout the whole course and compare some things. So we started out with linear functions. So this was your first introduction to graphs and sort of the style of graphing that we're going to do, where we've got these two variables, h and k. And h and k are like horizontal and vertical shifts. We could also take this and write it as y equals mx plus b, and that was called like slope-intercept form. And we used it a little bit, but actually I really like the y equals a times x minus h plus k. Then in addition to the linear, we had another version of this which was called the absolute value. And again, you had h and k, which represented a horizontal and vertical shift, and this graph looked something like this. You shifted the graph h units left and right and k units up and down based off of that initial graph. Then we had quadratics, and once again we had an h and a k, and our graph, it looked like a parabola. And again, this format was called vertex format, and the reason they called it vertex format was because h and k gave you your vertex. And we did have another format of this, y equals ax squared plus bx plus c, but we really liked running complete in the square on the standard format and converting it into this vertex format. But again, you notice a pattern. H and k is there, this horizontal and vertical shift. First conic section we looked at was a circle. And then we took the circle, and instead of having the same radius in the x and the y, we changed the length of the radius in the x and the y, and that created an ellipse. And this was the equation we had for an ellipse. And then we took that ellipse and we sort of flipped it inside out and we created a hyperbola. And so this was the equation for a nice circle. This was the equation of an ellipse. And this was the equation of a hyperbola. But notice all of these equations, everything that we've looked at for this entire course so far, has had an h and a k in it. So when we looked at the exponential function, we had a function that looks like this. If we were to graph the exponential function, there were a couple of key points. One key point was 0a and 1ab. So 0a was this point right here, and then here's the point 1ab, where a is the coefficient out in front of your equation, b is the base. And if we graph this, it probably looks something like this. And this is y equals a times b to the x minus h plus k. So the first thing that you did was you plotted these 2 points. You plotted 0a and 1ab. And then the second thing you did was you applied h and k. So if there was an h and k, you would take this graph and you would shift it left and right or up and down. I want to move this stuff down here. So this was the exponential function. Now let's talk about the logarithm. And so the logarithmic function is going to be y equals a times log base b of x minus h plus k. And so what are the 2 points that we want to plot when it comes to the log function? And remember that the log function is the functional inverse. And so what were the 2 points for the exponential function that we wanted to graph? The first point was 0a. So if that's the first point that we graph on the exponent, what's the first point that we graph for the log? A0. So we're going to plot a comma 0. So we're going to call this point a comma 0. The second point that we plotted with the exponential function was 1 comma ab. So if that's a point that we plotted with the exponential, what's the point that we plot for the log? ab comma 1. And that point is probably going to be right about here. Think about, again, the log is the inverse of the exponential. You're going to reflect it over that green dotted line. Your logarithm is probably going to give you a graph that looks like this. Y equals a log base b of x minus h plus k. The first thing you're going to do is you're going to plot a comma 0 and AB comma 1. Plot those 2 points. And then the next thing you're going to do is you're going to apply h and k. Right now we're showing you the graphs without any h and k shift. But what if we did have an h and k shift? So the blue function is the exponential function, and the red function is its inverse, or logarithmic function. And up at the top I've got some slider bars. So now let's play around with h and k. So let's shift it horizontal or vertical. And see how that moves? And let's move it vertically. So here is the graph of y equals log base 2 of x. Another way to write this would be 1 times log base 2 of x. So that means that a is equal to 1, b is equal to 2. So plot the 2 points. We need a comma 0, and we need ab comma 1. 1 comma 0, 2 comma 1. This has to go through 1, 0, and 2, 1. So it should look something like this. So we need a graph that looks something like that. So this guy's out, this guy's out, this guy's out, so I think it's this one. Very important that you plot these 2 points. Y equals log base 6 of x. A is equal to 1, b is equal to 6. We're looking for a comma 0, and we're looking for ab comma 1. So this is 1, 0. So this is the point 6, 1. And so your graph is going to look something like this. So this one's out, this one's out, this one's out, winner. So this one is log base 1/4 of x. A is equal to 1, b is equal to 1/4. So if you use this, we would go a comma 0 and ab comma 1. So a0 is going to give us, again, 1, 0. That's pretty easy. But ab is going to be 1/4 comma 1. So if we were to graph this, 1, 0 is no problem. That's 1, 0. How do you graph 1/4 comma 1? Your x-coordinate is 1/4, which is going to be like right here. And then you go up 1 unit. So this point right here is 1/4 comma 1. So what do you want to do with the negative? You said something about graph the negative. What do you mean? If you had 1/4 to the x power. So what I really like that you're doing is you're taking your knowledge of exponents and extrapolating it into logs. That strategy that we had. And this is where you employed that strategy. If you had 1/4 to the x power, this was piece of cake. This was 0, 1. That was easy. But then the next point right here was 1, 1/4. And you're like, how am I going to plot that? I don't know. And so what you did is instead of picking positive 1, you picked negative 1. And that would make this 1/4 to the negative first power, which is 4/1 to the first. And so you would plot this point, and it would be -1, +4, right? This was a strategy that we used when we were graphing exponents. So in addition to graphing a0 and ab +1, let's also graph a times 1/b -1. And so that is going to give you the coordinates for -1. So you go 1, 2, 3, 4. There's your 4. And then here's -1. It should look something like that. So clearly this one's out, and this one's out. But what about these two? Log of 1/4 of x, 1/4 to the x power. So this one's disqualified because it's an exponential graph, exponential decay. The graph on the left is logarithmic decay. So not only can you have exponential growth and exponential decay, you can have logarithmic growth and logarithmic decay. So this one is y equals log base 1/5 of x plus 4. So it looks like we've got an h on this one. So we've got a horizontal shift. But we don't apply that until later. So let's first graph those 2 points. So we're going to say a is equal to 1, b is equal to 1/5. So the point a comma 0 is equal to 1 comma 0, and AB1 is equal to 1/5 1, but that's going to be tough to plot, so we're also going to do the -1. So we'll do A times 1 over B, -1, which is going to give us 5, -1. So if we were to graph this, we get 1, 0, which is right here. We get 1/5 1, 1/5 1, which is up here. And 1, 2, 3, 4, 5, -1, which is right here. So those are our 3 points. We could probably sketch a graph that's going to look like this. And this would be the graph of y equals log base 1/5 of x. We now need to shift this to the left 4 units. So we're going to move this point to the left 4 units. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And the real graph is going to look something approximately like this. So you're out, you're out, you're out. I'd say that's the winning graph right there. So this is y equals log base 3 of x plus 2, 1 comma 0, and then 3 comma 1. So 1, 0 is going to be right here. 2, 3, positive 1 is going to be right there. Probably going to have another point down here, so this is going to be the log right here. Log base 3 of x. And now we need to take this entire graph and shift it up 2 units. So this guy gets moved up 2 units, this guy gets moved up 2 units, and you're going to have something that looks probably like this. This guy's out, this guy's out. It's a toss-up between these two. Which one do you like? Yep, I like that one. I don't like that one. This is actually a shift 2 units to the right, not 2 units up. So they're clever. They put in wrong answers knowing what mistakes you're going to make. You have 4 graphs here. Tell me about these 2 graphs. What type of function are they? Yeah, they're exponential, right? Tell me about these 2 graphs. They're logarithmic, right? So exponents in general kind of look like that, and logs in general kind of look like that. All right, fantastic. Tell me about the exponential graphs. There is a blue graph. So let's say that the black line has a base, let's say 5. Let's just make up a number. And the blue is going to have a base equal to something less than 5, right? How about 3? All right, now let's do red and green. And again, tell me about the bases. The base of the green and the base of the red. Well, remember this idea of inverse, right? Flipping it. On the black and the blue graph, which graph has the bigger base? The black line has the bigger base, right? What color, green or red, does the black associate with when you flip it over that line, when you find the inverse function? The red. These two are together. The black line and the red line have the same base. So the base on the red line is 5, and the base on the green line is 3. This is kind of weird though, right? Because you look at the graph and you think, well, the green line has to have the bigger base, right? The green line grows faster, and it's the opposite. Remember, these are inverse functions. So everything is flipped. So actually, the red line has a larger base. And in order to avoid this confusion, as b gets larger, as b goes to infinity, the graph hugs the axis. As b gets larger, whether you're dealing with an exponential graph or a log graph, that function hugs the axis. So when you look at the black line in the exponential has a bigger base. So that means it hugs that axis closer. Try to take the idea of steepness out of it. The idea of steepness works fine for the exponential, but then it bites you when you do logs. So the red line, the red log line, hugs the axis more tightly, so it has a higher base. So here are your 4 choices for equations. This one has a base equal to 10, and it's exponential. Base equals 2.7 and change, and it's still exponential. Tell me about this one. What is the base? 2.7, but it's not exponential. It's a log. And tell me about this one. Base is 10, but it's a log.